My name is Jaffa Haridano, and today we'll be discussing Lab 3 of Physics 2212, Magnetic Field of a Bar Magnet. The purpose of this lab was to measure the distance dependence of magnetic fields of a small bar magnet. We will use the Biot-Savart law to calculate both on and off-axis magnetic fields measured from a magnetometer. We will then create a computational model of our fields and compare our results. Fundamental concepts covered include using the Biot-Savart law. For this experiment, we will treat the bar magnet as a dipole and use the following equation, which calculates the magnetic field for a magnetic dipole. We will also use the following distance dependence relationship and measure our magnetic field B bar at different distances. We can plot this in the form of a natural log relationship to find n and then solve for our magnetic dipole moment mu. A brief preview of the results shows that the magnitude of net magnetic field increases as we get closer to our source or as distance decreases. Our measured dipole moment was 1.49 ampere meters squared, and our simulated magnetic field was 1.25 times 10 to the negative 5th Tesla. In this experiment, we treat the magnetometer within our phone as the observation point and the bar magnet as our source. Once again, we are treating the bar magnet as a magnetic dipole, and for this procedure, we had to download a magnetometer app onto our phone. Two types of measurements are taken. One's the on-axis magnetic field and one's of the off-axis fields. For the on-axis fields, which are on the left, we measure the distance between the magnet and the magnetometer for the following x components of the field. For off-axis, we solely measure the distance when our field is at 100 Tesla. We then measure the distance of the y component of just the Earth's magnetic field and then move the phone by this distance. We then measure the y component again at this new point. The following spreadsheet dictates our measurements, with on-axis data on the left and off-axis data on the bottom. A plot of the relationship between the net magnetic field and distance as natural logs results in the following linear regression. In this equation, our slope is equal to n, and the y-intercept is a constant k. By taking the log of this equation, we can replace b bar with our equation for magnetic field and solve for dipole moment mu, which in this case was 1.49. Some important notes are that for our off-axis data, we had to correct our y component by taking into account the Earth's magnetic field. So the following code was used to simulate our experiment, and we start by establishing our constants and creating a function for our magnetic field, and here we use the following equation for the magnetic field of a dipole. Next, I'm just creating the arrows for the on-axis and off-axis magnetic fields. And here you can see that we're using the perpendicular distance we measured in our experiment for the off-axis field arrows. And this is the final model with the magnitude of the net magnetic field being 1.25 times 10 to the negative 5th. So as you can see, the simulation and experiment results are quite different, and this could be due to a number of reasons. The main one being that within the lab room there was the presence of multiple magnetic fields, including iPads, iPhones, and other technology. And while we were doing the simulation on GlowScript, this code purely measures the field only from our source magnet. So what if we hadn't oriented our experiment to compensate for the magnetic north? Well, our magnetic field measurements would be different. The magnetic north contributes to the x component of our field, so we have to account for that. And if we try and move it to some intermediate angle with respect to the Earth's field, it would add to both our x and y components of our magnetic field, changing our answer. So what happens if we stick two identical magnets together? Then, by the laws of superposition, our magnetic field would increase. More specifically, it should double in magnitude if we have two of the same identical magnets. The direction, however, will remain the same, but the distance measured should decrease due to the increase in field. And some parting remarks are that we can treat bar magnets as magnetic dipoles, and we can look at the relationship between distance dependence and magnetic field and conveniently plot it as a linear regression. And then through this, we can easily solve for the magnetic dipole moment.